When advanced materials are subjected to intense pressure, predicting their macroscopic deformation requires tracking how their microscopic crystal structures warp and realign. To solve this specific scale-bridging challenge, material scientists rely on the viscoplastic self-consistent, or VPSC, model. We are going to derive the strict mathematical links this model uses to connect continuum spatial kinematics on the outside to mesoscale strain hardening on the inside. Establishing this link allows for a precise accounting of how anisotropic properties evolve as the material undergoes complex loading paths. The simulation begins by establishing the displacement field. This equation tracks the exact trajectory of a material point by subtracting its initial reference coordinates from its final position after deformation. This provides the basis for the deformation gradient tensor, F, which records the material's cumulative state using partial derivatives. We contrast this with the velocity gradient tensor, L, which measures instantaneous flow rate at the current moment. These two concepts merge in this time dynamics equation. The velocity gradient is defined by the product of the time derivative of the deformation gradient and its inverse. By multiplying by its inverse, the equation mathematically normalizes the deformation rate to the material's current spatial configuration, rather than relying on its starting point. This dynamic spatial normalization ensures the VPSC algorithm can handle massive, large-scale structural deformations without the mathematical framework breaking down. At the microscopic level, crystal plasticity presents a specific physical paradox. When crystallographic shear occurs, the act of slipping along a plane does not inherently reorient the axes of the crystal itself. To resolve this, the model deconstructs the deformation gradient into two distinct independent physical components. The pure stretch component captures the external deformation applied to the initial configuration, while the lattice rotation tensor represents the rigid rotation of the underlying crystal structure. To map how this slip is oriented in three-dimensional space, we use the midpoint form of the velocity gradient, introducing the Schmidt tensor. This tensor is calculated as the product of the shear rate, the slip direction vector, and the slip plane normal vector, locking in the geometric reality of the crystal. What engineers observe as a macroscopic velocity gradient is, in reality, a linear superposition of countless microscopic slip systems firing simultaneously. Applying that superposition logic allows us to completely decompose the velocity gradient into symmetric and antisymmetric parts. The symmetric component is the strain rate tensor, dictating physical shape change without inducing rotation. The antisymmetric component is the spin tensor, dictating purely rotational forces without altering shape. Rigorously decoupling shape deformation from structural spin provides the necessary mathematical isolation to accurately compute microstructural evolution during multi-axial stress events. With the state decoupled, the model must calculate how this geometry evolves continuously over discrete sequential fractions of time. This explicit time-marching algorithm dictates that the deformation gradient at the next time step is updated by adding the incremental deformation to the current state. Within this update sequence, the Kronecker delta acts as an identity tensor, establishing the baseline configuration right before the next stress increment is applied. The cumulative result of these continuous time steps physically maps the initial unit sphere into a deformed 3D ellipsoid. The mathematical engine driving this is the left Cauchy-Green tensor. Its inverse eigenvalues determine the ellipsoid's principal axis lengths, while its eigenvectors point to their directions. Shifting focus inward, the internal texture follows its own rotational logic, strictly separating lattice rotation from macroscopic rigid body rotation. Lattice rotation acts as a compensatory effect. It is the necessary reaction to absorb the non-compatible deformation caused by internal crystallographic slip. Because it acts independently from the rigid body rotation imposed by the outside environment, this compensatory lattice rotation serves as the true origin of internal texture evolution. We now move from the pure geometry of kinematics to thermodynamics, the physical resistance against that movement. This chart plots the Voce hardening law. It illustrates how flow stress increases rapidly at first, then approaches saturation as accumulating dislocation densities multiply and generate internal friction. The initial trajectory is shaped by two parameters: the initial critical resolved shear stress defining the yield point, and the initial hardening rate immediately following it. As strains elevate, the asymptotic hardening rate and target saturation stress model the material approaching maximum physical resistance. However, in real-world physics, these individual slip systems do not operate in isolated vacuums. They actively interfere with one another. This interference is captured as latent hardening. A moving dislocation on one slip system acts as a physical roadblock, impeding motion on an entirely different system, governed here by the coupling coefficient. To keep this highly coupled simulation stable, strict mathematical boundaries are programmed into the system. The principle of positive hardening dictates that the material must strictly harden over time, preventing the algorithm from calculating physically impossible softening responses. Enforcing these constraints to model dynamic recovery is necessary to prevent the algorithm from generating infinite hardening or non-physical, unstable stress responses. Testing the voice framework's flexibility pushes parameters to theoretical extremes. In the linear hardening limit, saturation parameters are zeroed out. Flow stress increases indefinitely, proportional to strain. Conversely, the rigid perfectly plastic limit removes hardening entirely, meaning plastic flow continues indefinitely without added resistance. This perfectly rigid limit mathematically mirrors the extreme thermodynamics of high-temperature processing, where actual materials yield steadily at a constant stress level. We began with basic continuum coordinates, decoupled tensors to isolate structural spin, and mapped the interference of microdislocations. By combining rigorous kinematic tensor decomposition with nonlinear voice hardening, the VPSC framework offers a unified method for predicting the microstructural evolution and survival of advanced materials under load.